So good morning to everyone, and thanks for coming to my talk. Thanks also to the organizers for inviting me here and for the nice setting. So what I'm going to discuss with you today is DICE, which is a research project funded by the European Commission under the Horizon 2020 framework. This is a project aimed at supporting small and medium enterprises in developing high-quality big data applications. So when we started this project back in 2015, big data, of course, was already there, but a lot of SMEs, in particular the smallest one, didn't have enough experience to come up with products in this space. And so there was an investment by the research community in Europe to come up with a toolchain that could accelerate the delivery of products in this space. And so DICE is a consortium of 9 organizations in Europe, several universities and several SMEs that are working together to come up with an open source, entirely free framework that you can use to build big data applications, taking into consideration also quality aspects like performance, correctness, security, and so forth. And of course, big data has been a big hype in the last few years, and we can think that we can solve any problem by looking at our data. Of course, there is a lot of inflation of expectations, but there is also the fact that since we are talking about big data, companies are using more and more big data processing platforms, solutions like in-memory analytics, platforms like Storm, Spark, Hadoop MapReduce. So in essence, there is a new range of products that can be offered on the market based on these solutions. And I want to give you an example of how this changes the game for small companies in particular. We have one company in our consortium, it's called Neffective, which is a company that operates in France, and they work in the legacy software modernization business. So they take applications maybe written in COBOL, in banks and in government, and they modernize them. And now suddenly, with big data, their customers realize that these legacy applications have also a lot of legacy data, and they can adopt platforms like Spark or MapReduce to analyze large volumes of this data to extract value out of it. And so for companies like Neffective, this is really a great opportunity. You can make a lot of money out of this, but suddenly you have to face the situation where your core business is about modernizing code, and you're asked to deliver new solutions based on platforms like Hadoop, Spark, Storm, and so forth. And so there are a lot of problems, of course. First problem is the learning curve. You might not have the expertise within your company to come up with good prototypes quickly. And this is a problem. Your projects might fail, the reputation you have with your customer might be affected by this. And so it is important, we believe, to offer tools and methods that can support companies like Neffective in doing this transition from their core market to the new possibilities offered by big data technologies. And just to give you a sense of the kind of problems that this company faces, in addition to the actual prototyping of these big data applications, there is also a problem of understanding how they work, how they can be tuned, how to estimate the cost, how to optimize the cost. So what you see here is an example of a configuration file for a Storm-based application, and as you see is absolutely crazy the number of configuration parameters that you have. Can be in the order of the hundreds, and not even the creators of these platforms really understand how these configuration parameters affect each other. And so you can try to optimize and tune the performance and reliability of your system by touching these parameters one at a time, but in the end, you don't really know what is the optimal configuration. And if you're in a SME where maybe you don't even have a quality assurance team, it's particularly difficult to come up with optimized solutions. So in addition to this concern that we want to address about helping them to accelerate the delivery to the market of products based on big data, there is also the fact that if you want to do things well, you need to understand this technology systematically, and if you don't have a QA team, maybe you're not in position to do this. And so there are questions that are very difficult to answer if you have a small team, you don't have QA support, for example, the scalability of your big data application. Maybe it's easy to tell if a platform scales as you want. You can do some benchmarking, but when you consider your specific workload, your specific application, it's more difficult to understand if it will scale. Maybe you're not just using a single platform, maybe you're using multiple platforms. And so it's difficult to anticipate scalability. It's difficult to choose technologies. You see, with big data, we have a broad offering of data processing platforms, and it's not always clear which alternative is better. And if you pick a technology, you don't want to be locked in that technology, and then tomorrow there is another technology coming out that would be better. So you need to factor in also the risk of being locked in. And so how do we come up with a methodology that allow change if we need it, to change the technology? And also the architecture, as I said, if you use multiple technologies, it might be difficult to understand what is the optimal architecture for your complex distributed application. And if you have a guess, you may do some tests, but how do you really verify that you pick the best one? There may be too many alternatives for you to choose from. And also, over time, the expectations you have in terms of performance, reliability for your application might change. Your customer might have set with you service level agreements that evolve over time. And so you need to adapt the design and the resources that are assigned to your application. And so we need a toolchain that supports this. And so a bit to recap on the dimensions that we have to consider when we design a toolchain for big data applications in the spirit of DevOps. Certainly we need to, first of all, be able to characterize the properties of the data to some extent. Traditionally, in software engineering, data, I would say, is not a first-class citizen. You can describe, for example, the relation between different data sets. You can describe your database, but in a way, properties like volume, velocity, location of the data, they're not first-class citizens. And now with big data, they become first-class citizens. So we need to change their role in the software engineering process. Secondly, DevOps. We are all persuaded that this is a good development. And so when it comes to big data platforms like Spark, Hadoop, Cassandra, and others, we might need to extend some of the tools we have to support these technologies. And this is partly the work we've done in DICE. But there is also this dimension that we are not happy with just delivering prototypes. We want high-quality prototypes. And so we need also tools that are able to reason on performance, reliability, and other qualitative properties of big data applications. And so with DICE, we tried to cover these aspects. So we came up with a framework which roughly follows the methodology you see here. So the idea is that you can design your application. You have an environment based on Eclipse, where you can design in a model-driven fashion your application. And then you can verify, simulate, and optimize cost, consider what is scenario for your architecture before creating the initial prototypes. And then once you have a prototype, so you code, you create your prototype and you deploy it. And with the deployment, you get your monitoring platform that feeds back runtime information to your IDE. So from within the IDE, you can understand how the application prototype is performing, what are the performance anomalies that you observe, and then we keep iterating until this application is ready for production, and the cycle can also continue in production. And certainly there are different perspectives when you look at the users, the user profiles for a solution like this. There are developers who are primarily interested in coding, and so inside Eclipse you can use your favorite coding tools, but there are also architects which are more concerned with the relationships between the components of your application, and so they want to understand the high-level structure of the application. They might use model-based approaches like UML or others to characterize the dependencies between components, their relationships. Then, of course, you have ops, which might not like at all UML. And then you have people concerned with testing, either functional testing or non-functional testing. So within DevOps, we have this notion that we want to bring together people from different teams and share the process. And when we try to put together all these different perspectives in a say, naive way, what we could try to do is that we adopt a series of tools, a set of tools that covers the needs of these different people, and we put them together in a team. But the result is that they are not really sharing a unified understanding, a unified view of the system. Of course, they can talk with each other, but when we have the possibility to deliver a unified tool chain that is used by all these users, developers, testers, and so forth, I think we can do better. So DICE tries to come up with the notion that we should strengthen the model component of DevOps. When you look at model-based operations, the progress has been already made in terms of representing the relationships between the nodes and deploying automatically complex applications, say in the cloud. But now we want to have a holistic solution that covers both the development and operations with an emphasis on this model-driven aspect. And we emphasize the models because they represent the shared understanding between the different people, the different users of this framework. And so in DICE, as I already said, we create big data applications, and we focus in particular on a set of technologies like Hadoop, Spark, Cassandra, and Storm. And we assume that the applications are deployed either on a private cloud or on a public cloud, like, for example, AWS. And then what we have done is that we have created an IDE by extending Eclipse, an environment for development, where we have encoded our methodology. You have cheat sheets that guide you through the application of the DICE methodology. And perhaps most importantly, we have an extended UML profile, which brings UML in the space of big data technology. So you can describe the topology of a Storm application. You have the mappers, the reducers. So you have a lot of elements that you don't have in standard UML. And now in this Eclipse environment, you also have several plugins that allow you to expect the quality dimensions related to performance and reliability and correctness through techniques like simulation, verification, and numerical optimization. And then what is important is that you can automatically transform these models that describe your application into a blueprint for deployment on the cloud. And so we use Cloudify and TOSCA for this. We have also support for continuous integration. We have Jenkins, we have testing. And once the application is running, it is running together with a monitoring platform that continuously collects performance data and using a ELK stack, and continuously analyzes this data to find performance anomalies and bring back this information to the IDE. So this is the conceptual idea, that we have a feedback loop, and we are trying to cover through models, both the space of dev and ops. And so how does it look like? Well, when you look at the dev perspective, you have, besides the code in your IDE, you have also the possibility to open models, which represent concepts also related to the ops domain, like deployable artifacts. And you have the set of your plugins for monitor, optimization, simulation, and so forth. So within the IDE, you can have a look at all these monitoring metrics, or run a procedure to optimize the cost, or find an architecture, an ideal architecture for your application. And since there is this difference in perspective by different users, we also have a number of dashboards in the operational space, which are more convenient for systems people, for system administrators. So we have Kibana dashboard, Jenkins dashboard, and Cloudify dashboard for deployment. So what is happening behind the scene more in the details? Well, the idea is that we have a hierarchical set of models to describe this big data application. So in the very early phases of design of your application, what you should do is to clarify what are the high-level functionalities of your application, what are the performance requirements, and a model that does this, we call it a platform-independent model. So you see here an example for a word count application. We might require an average response time of 30 seconds and do a very simple generic model that describes a computation node, a storage node, and a source for our data. And then progressively, as we go on with the prototyping, we can pick a technology, and actually the previous model I've shown, you can already come up with the initial simulation to get a high-level qualitative idea of what could be the performance. So you need to guess some numbers about the execution times of different components, but before the application exists, there isn't much you can do better. And so with that information, you might start to get an idea of what technologies you would like to pick based on simulation results. And now we enter into technology-specific models where you can describe how you would structure the different components, for example, of your Hadoop application. So you would have mappers, reducers, you would have storage based on HDFS file system, and so forth. And so these abstractions are extensions of UML that we provide with DICE. And then you have to choose a concrete deployment. And this is the last level of our models. So basically, we assign these logical components for the architecture of our big data application to concrete resources like VMs that run, say, on an OpenStack cluster. At this stage, our tools for quality testing can help you, for example, deciding how many resources you need. So if you provide estimate of the execution times and how many users you have for your application, we have techniques to automatically translate these architectural models into mathematical formulations that run optimization programs to give you an estimate of the best sizing that you can do for your resources. If you're using spot VMs, for example, you need to bid for a spot price. Which price are you going to bid? Or is it better to use reserved VMs instead of on-demand VMs? So these kind of decisions are supported by our optimization tools, and you can consider a cost optimization or a performance maximization objective. And now, after you have basically gone through these initial modeling steps, you can automatically transform your deployment model with the resources that have been assigned by this optimization tool into a TOSCA blueprint. So in parallel, you need to develop your application. We do not give you any special API to create your application. You develop it as you want, but these models live in parallel to your code. So once you have a jar that you're ready to deploy, and you have your deployment model, this last the DSM layer of our UML models, you're ready to actually deploy your application. And so what we do is that we have a model-to-text transformation that creates a TOSCA blueprint. And so in TOSCA, we have essentially a model-based language to describe nodes and their relationships and automatically deploy our complex applications in the cloud and configure them based on this TOSCA specification. We use in particular the Cloudify orchestration engine. And what we have done within DICE is that we have extended the TOSCA blueprints that specify how the different nodes of your big data application should be configured to support a broad range of big data technologies like Spark, Storm, Hadoop, Cassandra, Kafka, and others. And so these templates that we provide in DICE for these technologies allow you, for example, to specify the configuration you want for a specific node, and then Cloudify will take care of materially deploying this node in the cloud and applying this configuration for you. And so from the high-level point of view of the developers, you just specify your preferences in the models, but then they get automatically translated in this TOSCA blueprint, which if you want, you can edit manually, but in principle, you don't need to. And now this is the point where we are moving into the ops side. So we have this TOSCA blueprint, and so we have converted our view from the developer side into a concrete model that is executable in terms of deployment and configuration. And so in DICE, we have a set of tools in the runtime environment that cover not just the deployment and the continuous integration, but also monitoring, quality testing. So for example, we load test stream processing systems. We are able to reproduce, for example, loads based on historical data, or create new loads to verify the scalability of your application. We have fault injection tools similar to Chaos Monkey. And we have some advanced capabilities that will show something more about this later, about automatically tuning the configuration of your big data application, which is the difficult task I discussed at the beginning. And now, as I said, monitoring data is continuously analyzed, and we look for anomalies related to performance, to privacy, but also we try to bring back in the models that are available to the developers the information that we have collected at the runtime. So at the beginning, I told you, when you simulate your application, you need to guess the execution times of the different requests. But now, since you are running this application and you are releasing new versions of your application over time, you can just take this data from the monitoring platform. So we have inference algorithms that extract this execution time from the observed performance of the application and annotate back this information in the space of the developer so that you are really closing the loop. And I want to show you some applications of these to concrete demonstrators. So the first application is about configuration optimization, which is the case I shown at the very beginning. So you have this huge configuration file, and imagine if you have 100 on-off options, the range of possible configuration you can have for your system is 2 to the 100, right? So it's an astronomical number. And now, how do you deal with this situation? How do you come up with a good configuration? Well, we examined this problem in particular for Storm-based systems, and we had a case study in our project offered by a company from Greece called ATC that works in the space of news and media. And they have a platform that supports content creation for newspapers. And in particular, part of this platform that is called the News Asset is interfaced to Facebook and Twitter. They take, for example, tweets, and they continuously look at trends in the information that flows on Twitter in order to inform journalists about trends and possible news to report. And so behind a system like this, there is a combination of multiple big data technologies like MongoDB or Redis, but primarily their logic is on a Storm cluster. And so using DICE, what they've done is that they have described the architecture of this system, in particular the storm topology using our models. And then, so you see here, for example, bolts and spouts for this storm topology. But then from within the IDE, they're able to open a panel which is called DICE configuration view, which lists all the possible configuration parameters from that list of 100 that I shown before. And now what they do is that they can express ranges for these parameters. They say, you know, I don't know which are the best allocations of these parameters, but are within this range. And so you can do this for a number of parameters. And then as you deploy, since everything is automated in the deployment, we can really bring you know, the consequence of this to the point that we can automate also the tuning of these configuration parameters. So what you could do is that you can have a batch process maybe at night where you explore alternative configurations for your system. And what you do is that you have maybe a reference workload and a system that continues to test this reference workload against the different configurations. But if you have 2 to the 100 possible configurations, you won't finish them all. And so what we do is that we use advanced machine learning to come up with the decision of what is the next configuration to pick. And so when you do an experiment, you are collecting, let's say, a point. So this point is giving you the performance of the system with that experiment. And as you collect the points, what we do is that we use advanced techniques in machine learning that is called the Bayesian optimization that creates a surface that tells you, as you change these configuration parameters, what is our expectation that, about, say, the latency of the application. So we are creating a model that captures our experimental data to predict the optimal choice for the next experiment to run. And the characteristic that makes this Bayesian optimization special and different from other black box optimization methods is that it is especially engineered to run as few tests as possible to get a good near optimal configuration. And so we tried this out, in particular against a storm testbed. And so in this diagram you see throughput and latency for the storm application we are discussing related to news. And this was, so each point basically gives you the performance of your system. And so we start from a default configuration in this region, so low throughput and high latency. And then we tried to ask to an expert, how would you tune this system? And the expert was giving us a configuration in this space. But as you run automatically this system, because it can continue to test a new configuration, we end up exploring after about 100 tests. We reached a region where we had very low latency and high throughput. And so you see that basically these techniques that in essence depend on our ability to automatically deploy the application can increase substantially the quality of the final application. We can auto-tune applications. Another example I want to give quickly is about deployment. So we had a case study about an application that is used to drive boats in ports through a technique called geofencing. So you create basically a corridor for your boat to enter the port without hitting other boats. And there is a signaling system between boats and ports that allows to track their position continuously. And one of the companies in our consortium has a stream processing system that uses this information to support the port operators in guiding the boats, the ships in the port. And so they use DICE to bring this application to the cloud and automate their deployment. Before they were simply sending their engineers to the customer side and do things manually. And now they embrace DevOps practices. And so what they do is that they have come up, even though the application is already existing, they come up with a schematic view using our models of the deployment structure of the application. And so you see here components like Rabbit and Q for the application, and then they convert this model into a TOSCA blueprint. So this step you've just seen is this conversion. And now you have a file with all the deployment information that can be uploaded to our deployment services. So it's this archive gets uploaded, and then you launch the deployment of the application, and after some minutes, it starts creating the virtual machine on the cloud, it starts installing the application automatically and configuring according to what we requested in our models. And then with the application, so you see here the application running, you get also the monitoring automatically installed with it. So you see here the monitoring dashboard. And so you can continuously monitor for performance anomaly. In the case of a stream processing application, you can also look at the volume and the velocity of the data that is coming in. And actually, you can even geolocate it. So in relation to these ships, you can tell which ship is sending more data at which rate. And you can check also for CPU burst and problems related to the runtime performance. And so with this company, basically, before they were taking 8 to 16 hours to deploy their application in production. First attempt they used DICE, it took 5 hours, and then now when they go to the customer, typically in 20 minutes, they can bring up the application. I just want to close with a few more slides on cost-cutting concerns. So one benefit of our model-driven approach is also related to privacy. So we have one application in our consortium, one demonstrator that is related to tax fraud detection, which is an important application use case of big data. And so Neffective, the company we discussed at the very beginning that wanted to profit from legacy big data, is trying to apply Spark technologies to the analysis of tax data. And so they have to process even millions of tax data for different citizens. And of course, there are a lot of privacy concerns in doing this. But with an approach like ours, you can specify within the models different roles and different permissions for different users. And as you deploy your application, these permissions, these access control rules are actually applied automatically to the systems. And moreover, the privacy model is shared with an application at runtime called the trace checking service that continuously analyzes the log, trying to find out if there has been a violation of these rules as evidenced by the logs. And so this is an application of this notion that you can share models between the development space and the ops space. So I want to stop here. So the key message that comes out from my presentation should be that the model-driven approach really helps gluing development operations and quality assurance. You have a truly shared understanding of the system based on the models between the different teams. And it's very easy through this model-to-model transformation to reason and enforce quality concerns like privacy and performance. And in our experience, it's particularly valuable to companies, the model-driven deployment. They really like the fact that they just draw a few boxes that can deploy on the cloud very easily, even if there are no deep understanding of the underpinning technologies. And moreover, there's no the templates they define for the deployment that can be reused, and that's very valuable. And lastly, I've shown you more researchy feature of our framework, this configuration optimization that leverage DevOps to optimally tune a big data application. So thank you very much for your attention. I'm taking questions.
Thank you. Questions? Do we have any questions? Please raise your hand. Don't be afraid. There's a question one.
I've got a question. how easy is it to extend this platform, especially on the HDUP stack? For example, I'd like to add HBase. Is it possible to do right now?
Yeah, is extensible. It depends on what you want to do exactly. If you want to extend the models, you need to have some basic understanding of how to extend a UML profile. But we provide many examples of, it's all open source, so you can see how we extended this model for the different technologies. And actually, we are forming now several partnerships to continue the development of this solution, so you can also come to us, and we are happy to talk with you and support you in the extension.
Another question?
I wonder how long does it take to perform those optimizations? This, for example, 100 that you mentioned. I know that it's dependent on the case, yes, but on average, how long does it take to perform all those computations?
That's a very good question. It depends clearly on the workload and the application type. If you have a batch application like MapReduce, even a single experiment can take several hours. And if you instead run a stream processing system, the workload can be quite fast to execute. So it's up to you really to define the reference workload. What we provide to you is a technique that tries to speed up as much as possible the identification of a good near optimal solution. But then if you imagine to set up, say, a batch process at night that repeats experiments for 1 week or two, you certainly arrive there. In our case, for this experiment with Storm, it was taking basically 1 night to come up to that optimal solution. But it really depends on the workload.
Okay, one more. Okay, can see any hands? Because you said that you just released the final version, right? So what is the roadmap? What do you plan to do in the next version?
So the project is going to finish in January, but we have created basically methods to continue working on these activities. So we're going to commercialize 2 products based on DICE, one to design stream processing systems, the other for Spark-based applications. So we want to bring this forward in terms of commercialization, but the basic platform is free, open source, non-viral license, so that's accessible to everyone. But I would say that our future is more in the commercial direction.
Okay, right. So thank you so much for your talk. Big applause, please.